dear learners. Welcome to SWAYAM NPTEL course on Methodology of Educational Research, and I am Dr. Saritanand from Department of Education, Vinay Bhavan Vishwabharati, Shanti Niketan, and today we will talk about the module 40 on determination of sample size and concept of sampling error and sampling bias. This is lecture 40, and before going to the lectures, let us see the concepts covered. Earlier we had discussed about the comparison between the probability and non-probability sampling. Then we had covered the mixed sampling design, where systematic sampling and how the skip intervals can be calculated, about the geographical square grid method we have covered, and also we have gone through the advantages and disadvantages of systematic sampling. Now we will start with our today's topic, that is determination of sample size. When we are talking about the sample design, sampling technique, sample size, then determination of sample size is very critical, important in methodological decision in research, as it directly affects the accuracy, reliability and generalizability of the study findings. According to Israel, and he asked the question that what size sample do I need? As a researcher, does not have a single fixed answer. Rather, it depends on the several interrelated factors such as the purpose of the study, population size, acceptance level of the sampling error, and the risk associated with the drawing incorrect conclusion from the sample. So, if we are talking about the determination of the sample size, there are few criteria for determining the sample size. According to Israel, in 1992 identified 3 essential criteria that must be specified before determining an appropriate sample size. What are those 3? The first one is level of precision, second one is confidence level, and the third one is degree of variability in the population. So, let us see. The level of precision, also referred as the sampling error, indicates the range between the within the true population value and expected to fall. So, it is commonly expressed in the percentage terms of the plus minus 5%. A smaller margin of error requires a larger sample size to ensure more accurate estimation of the population parameter. The second type is the confidence level. It reflects the degree of certainty that the sample estimate represents the true population value. Drawing on the central limit theorem, Israel explains that at 90% confidence level, or the 95 out of 100 samples drawn from the sample population will contain true population value within the specified precision range. It means that the 5% plus or minus error chances are there. In higher confidence levels such as 90%, 99% reduce the risk, but require larger sample size, whereas lower confidence level increases risk and reduces the required sample size in the research. Here in 99% level of the confidence says that the 1% error chance is there, plus minus 1%. So, we have to go for the I suggest it at the PG level, go for the 95% of confidence level in your researches. The third type is the degree of variability. It refers how heterogeneous the population is with respect to the characteristics being measured. Population with greater variability requires larger sample. When the population variability is unknown, Israel recommended assuming maximum variability 0.5. So, as it produces a more conservative and statistically safer estimate of sample size. So, strategies for determining the sample size. Because I have prepared this lecture with the help of the document of the Israel, that is why I am quoting again and again the name of Israel. He outlined the 4 practical strategies of determining sample size. The first strategy is conducting a census, which involves including the entire population at the sample. This approach is particularly suitable for the small population only, generally 100 or 200 or fewer. So, it eliminates the sampling error and yields the complete population data. The second strategy is to using the sample size of similar studies. Reviewing prior research can provide guidance to typical sample sizes and used within a discipline. However, he cautions us that this approach should be used carefully, as methodologically its weakness in earlier studies may be inadvertently replicated and may be affecting your research. The third strategy involves using published sample size table, which present predetermined sample size for a specific combination of the population size, confidence level, precision and the variability. Israel provides in his document that the tables that assume a 95% confidence level and maximum variability level 0.5, these tables are particularly useful for applied researches and evaluation studies, provided that the assumption of normality are reasonably met. So, if we are talking the fourth point in this strategy, the rigorous strategy is the use the statistical formulas to calculate the sample size. So, Israel discussed about the Cochrane's formula for large population, which incorporates the desired confidence level, precision and estimated population proportion. When dealing with the smaller populations, the sample size can be adjusted using the finite population corrections, which reduces the required sample size while maintaining the same level of precision. He presents the Yamin's simplified formula, which assumes a 95% confidence level and maximum variability and is widely used in the social science and educational researches. So, let us look at the formula for the calculation to determine the sample size. The sample size calculation using Cochrane's formula given in 1963. For large population, Cochrane's formula is used to calculate the sample size for proportions. So, here this is the formula where you can see that the n is required sample size and z is the standard normal value, p is the estimated for population proportion, q is 1 minus p and e is desired level of precision. So, n is sample size is equal to z square p q upon e square. The illustration of this formula can be, suppose we can take the example of any sample, and in this example you can see that 90%, 95% confidence level is having plus minus 5% precision and maximum variability of 0.5%. So, if we are going to calculate this 0.5% variability, so sample size will be having 385 respondent is required in the large population. I have missed the population number maybe here. So, if the population is having the finite population correction, when the population is small, the sample size can be adjusted using the finite population correction formula. And what is that? That is n is equal to n 0 upon 1 plus n 0 minus 1 divided by n, the capital N, this is the population. So, here n 0 is sample size and capital N is the population size. If the population size of farmers is 2000, then if we follow this formula, n sample size is equal to n 0 upon 1 plus 101 minus upon the capital N. So, calculated value will be almost 323, which is nearer to the previously calculated value. So, simplified formula of Yamin in 1967, she also mentioned that the 95% confidence level and maximum variability, and given the formula n is equal to capital N upon 1 plus n multiplied by e square. So, here you can see that the n, small n is the sample size, capital N is the population size, and the E is the level of precision. And the same example, if the population size of farmers is 2000 can be calculated, and the calculated value of the simplified formula is giving the sample size of 333 farmers from the population of 2000. So, that is also nearer to the previous calculated value 2023, sorry 323. So, this formula is widely used in educational and social science researches due to the its simplicity. It is a simple formula, and if we go by the sample size for mean, so there is another formula for the continuous variables. Sample size may be calculated by using the n0 is equal to z square into sigma square upon E square, where the n0 is the sample size, g is the abscissa of the normal curve that cut off the area of sigma at the tails, and E is the desired level of the precision in the research, and the sigma square is the variance of the attribute in the population. So, this formula can be also adopted, but the previous formula is very popular in the field of education. Now, sampling error. Sampling error, according to A.K. Singh in 2012, he said that as the reader must have gathered by now, sampling refers to the process of drawing a limited number of cases from a population. Whatever the sampling procedure used, the sample must represent as far as possible all characteristics of the population that are related to the problem under the study. A statistical measure calculated from the sample is known as statistic, note it, and the correspondence measure, which is usually unknown as based directly upon the population, is known as parameter. So, statistic is frequently referred to as an obtained measure or derived measure. A mean calculated from a sample of population is called a statistic mean, and the value of mean based on directly upon the population is known as parameter mean. And the difference of this statistic mean and the parameter mean is called sampling error in the research. So, a sampling error is the difference between the parameter and the statistic. As Lindquist in 1968 has put it, that a sampling error is the difference between the parameter and an estimate of that parameter which is derived from a sample. So, a sampling problem is said to be existing whenever the conclusion obtained on the basis of limited number of individual samples are applied to a large number of individuals called population. Such generalization conclusions are known as the statistical inferences, and the higher the sampling error, poorer the statistical inference, and vice versa. Greater the lesser the sampling error, greater the inference. The term sampling error does not suggest any mistake in the process of sampling itself. Rather, it merely suggests chance variations which are inevitable when number of randomly selected samples are taken from the same population. Due to this sampling error, making an estimate about the population characteristics from the sample characteristics no longer remains an exact process. It has been observed that the sample statistic does not ordinarily agree with that obtained from the second, third or fourth sample or with the population parameter. The amount of fluctuation from the sample error depends upon the following two factors. What are that? The variability in the population and the size of the sample. If the nature of the population is such that is not stable and tends to vary naturally, then successive samples taken from the sample population over the time will tend to differ. So, there are certain statistics which tend to fluctuate less than others in successive samples, and hence the sampling error is less. For example, in sampling from a normal distribution, the mean of the standard deviation fluctuates less than other measures of central tendency and measures of variability. Hence, these two are more reliable than other similar measures, because the variability is there. Hence, these two are more reliable than other similar measures, because they approximate more closely to the corresponding population parameter, and hence tend to fluctuate less from sample to sample, and thus produce the least sampling error. This is whole content is from AK Singh. And in most sampling situations, there are three types of important distributions which are concerned to the reader in order to have a clear cut idea about the application of sampling error. So, they are the sampling distribution, the population distribution, and the sampling distribution. These three terms may be explained with an example. Suppose we wish to know the mean intelligence score of the workers age range of 20 to 45 years in the Tata iron or steel factory or any other factory. Further, suppose that the total number of workers in this given age range is 30,000. Owing to time and money consideration, we may decide to take a random sample of 300 and administer a standardized test of intelligence. The obtained score on test of 300 workers expressed in frequency distribution will be called as the sample distribution. Thus, the sample distribution is an observed distribution which can be described by any descriptive statistics. Hence, sample distribution is the concrete distribution in any sampling situation. However, if we decide to administer the test of intelligence on the whole population, that is on 30,000 workers, we shall be getting a set of 30,000 scores. If we convert this set into frequency distribution, this will be known as the population distribution, because we are not taking the sample, we are working on the whole population. Ordinarily, the form of and the parameters of the population distribution are not known. However, we can infer them on the basis of the sample distribution. If the sample distribution is normal, it can be inferred that the population distribution is also normal, ascribing any irregularities in the sample distribution to the sampling fluctuations. So, the inferences drawn regarding the population distribution on the basis of sample distribution may not be correct due to the sampling error. In the above example which we have discussed, we do not have the distribution may not be correct due to the sampling error. In the that example, we do not have the fixed mean or fixed standard deviation which would be obtained again in the second or third sample of 300 from the population. If we have to take say 100 sample of 300 each, we would be getting 100 different means, 100 varying standard deviation, because we have taken the sample of 100. If all the 100 means and 100 SD are grouped in frequency distribution separately, we would have an exact sampling distribution of mean and the standard deviation in the population. So, by listening it will be little tough, as this is not done. Sampling distribution is theoretically or idealized distribution which may be thought of as a distribution which would be obtained if the values of a given statistic were computed in all possible numbers of the sample of given size actually taken from the population. So, any statistician have been able to determine the sampling distribution of the majority of the commonly used statistics in the samples taken from the normal population. When the sampling distribution of the statistic is known, it is possible for the investigator to determine the relative frequency with which different sample values tend to occur in random sampling from a population in which the statistics have some of them assumed or hypothesized. After knowing the relative frequency, the investigator is able to know the probability that a particular sample value has resulted from the sampling fluctuations or the chance. So, ultimately by knowing the probability figure, he or she will be able to judge the soundness of hypothesis regarding the value of statistics in a population. So, other factors of sampling errors are also there, like many mistakes and errors in social sciences researches are there, misleading and biased sampling. A sample which does not represent the population is called biased sample. According to the Yule and Kendall, the bias may be due to impactful instruments, the personal qualities of the observer, or defective techniques and other cases due to which the bias sampling is coming. Like experimental error, it is difficult to eliminate entirely, but the usually may be reduced to relatively small dimensions by taking proper care. This is said by the Kendall, Yule and Kendall, and when doing research, it is important to know all about errors that could happen during the data collection and review phases to make sure that the results are correct and reliable. There are two main types of research errors. We call it sampling error and the non-sampling error. So, when doing research, it is important to think about both the sampling and non-sampling errors. It has its own effect on the accuracy and dependability of the results of the research. For probability samples, sampling theory allows you to calculate the expected amount of the error given in a particular sample size, method and specific statistics of the interest. In general terms, the sampling error is for a statistics can be defined as the standard error is equal to under root variance upon n, that is equal to SD upon under root n, that variance is SD, standard deviation, and here n is equal to sample size, SD is standard deviation, and as the sample size increases, standard error of statistics decreases. As sampling variance or dispersion of a static increases, it does its sampling error. So, greater the sample size, lesser the error. Lesser the sample size, greater the error. This is the relation of this error. Then sampling error decreases rapidly as the sample size increases from a few hundred about 1000 respondent. However, there is rarely any reason to select larger samples while comparing the increased cost of survey with reduction of the sampling error. If you are going to calculate, it will take the sample size. In the next session we can discuss the formula for the standard error of proportion is simply easy to apply. What is that formula for standard error? That is under root p into 1 minus p upon n. Here this p represents the proportion of successful favorable response, those who receive the benefits, and the q is equal to 1 minus p represent the proportion of the failures who did not receive the benefits, and n is the total number of respondents, and thus the standard error of a statistic is greatest when the p and 1 minus p is equal. So, which occurs when each is 0.5 or 50% of the sample. So, sampling error happens because you are only looking at a group or not the whole population. You can reduce this error by using the right sampling method. Other types of errors called non-sampling errors, and are used by a bigger range of issues in the research process and need strict quality control measures to be fixed. While both types of errors can affect how accurate the results are, they come from different sources and need different ways to be fixed. For reliable and trustworthy study results, it is important to fully understand the difference between those two types of mistakes and how to use strategies to lessen their effect. The data collected by sample survey represent only a fraction of entire population. So, it is inherent that some of it may lack accuracy. This inaccuracy is generally referred as sampling error or error variance. By employing more sophisticated sampling techniques such as stratified or cluster sampling, or by increasing the sample size, sampling error can be quantified and minimized. On the other hand, non-sampling errors have nothing to do with the sampling. So, they arise from other stages of the research process. This type of error can occur at any stage from data collection to data processing, and it may be more difficult to detect and correct. Some of the issues that are not caused by the sampling, including the incorrect measurement, poor data entry, non-response bias and interviewer bias. For example, if those who respond to a poll question do not comprehend it, or if inaccurate data is captured, the ultimate finding will be erroneous and lead to incorrect conclusion of the research. So, non-sampling errors can sometimes be more damaging than the sampling errors, because we can control somehow the sampling errors, since they might alter the overall outcome of the study by introducing the bias. The presence of random variations in the sample implies that it may not accurately represent the entire population, and this is the underlying cause of sampling errors. To estimate the magnitude of these errors, it is common to express them as a confidence interval or margin of errors. Conversely, non-sampling errors frequently occurs unexpectedly and can be attributed to the several factors such as poorly designed survey instrument, fatigue of the respondent, no interest of the respondent, problem is in the data processing, or deliberate data falsification. That is called misconduct, or we can say the data hampering. So, given the multitude of categories and degrees of complexity associated with the non-sampling errors, it is imperative to engage in meticulous planning, meticulous data gathering and comprehensive data verification in order to mitigate their impact. This was all about the sampling error. Now, there in our syllabus there is a term sampling bias. So, let us try to understand the term sampling bias. This sampling bias is a systematic error in statistics where some members of a population are more likely to be included in a sample than others, resulting in a non-representative sample. This skews the research result and prevents accurate generalization about the larger population, thereby compromising the study's validity. It means that the technique used to obtain the individuals to be in the sample tends to be favor one part of the population over the another. For example, a survey of high school students to measure teenage use of illegal drugs will be biased sample because it does not include the home-schooled students or dropouts. A sample is also biased if certain members are underrepresented or may be overrepresented relative to the others in the population. So, this sampling bias also known as selection bias. It is when your sample is unrepresentative and will not provide the right feedback to support the goals of the survey research. So, that is selection bias. Some samples forget to include in the right target customer market segment. This can lead to the inaccurate data results. So, this was about the sampling or sample bias. Now, we can conclude that the sample size determination is the foundational methodological decision that directly influence the validity, reliability and generalizability of the research findings. An appropriately determined sample size ensures the sample adequately represent the population while balancing the statistical precision with practical constraints such as time, cost and accessibility. Sampling error is an inherent and unavoidable aspect of the sample based researches, arising from the fact that only a subset of the population is studied. A smaller margin of the error enhance the accuracy of the population estimates, whereas poorly calculated sample size increases the likelihood of inaccurate conclusions. So, in contrast, in the sampling bias poses a more serious threat to research validity, as it results from the systematic flaws in sample selection rather than chance. Unlike sampling error, sampling bias cannot be corrected by increasing the sample size alone. So, careful selection of the sampling technique and transparent procedures are therefore essential to minimize the bias and ensure the representativeness of the conducted research. So, this was all about the today's lecture, and now these are the references. I hope you will go through it, and this if you want to go for the detail regarding the sample size decision, you can go through the given link also in the reference. So, keep learning. Thank you.